This is Jeff Badge of the Grinding Doc, and this is the first part of a series I'm going to do, a 10-part series. And it's looking at as sort of a tribute to the great academic papers of a guy named Stephen Malkin. And if you work in grinding, especially if you're in academia, you will definitely know who Stephen Malkin is. Stephen Malkin, in my opinion, was probably the greatest grinder that ever existed, at least in terms of grinding research and adding to our understanding of grinding. Some people may take offense at that. Some people maybe think they're the greatest grinder in the world. That's fine. Send me an email and tell me why you're the greatest grinder in the world. I am right now, though, I'm a believer that Stephen Malkin was the greatest grinder in the world. Passed away a few years ago. My goodness, more than a few years ago now. And he went to MIT. I think he did his bachelor's, master's, and then eventually his Ph.D. at MIT, Massachusetts Institute of Technology. Worked various universities, was in Israel for a while, came back, and I think of him at the University of Massachusetts at Amherst, where he did most of his time and he had his grinding lab. He's got his own Wikipedia page. If you got your own Wikipedia page, you must be somebody. I don't have a Wikipedia page. And he wrote a book in 1989 and then a newer version some years ago with Cheng Guo, Grinding Technology, one of the greatest books out there. And then this is right here. I have one of his first article back in 1970. I think he finished his PhD about 69, 70 at MIT. And this is the paper we're going to talk about today. Some of the grinding greats in history, they're going back to the 1910s. There was a guy named Alden. There were others, Guest. And then in the 1950s, we had Tarasov at the University of, Norton Company. And then we had MC Shaw was one of the greats, and he sort of took knowledge from turning, milling, and drilling, kind of chip formation, and then applied it to grinding. Other guys, but Malkin, I would say, was when we first started kind of looking at things scientifically, looking at things from first principles based on material science, Newtonian mechanics, physics, heat, F equals ma, P equals W over T, all those fundamental things, conduction, convection, cooling, heat into the part, all that stuff. And he did it from first principles. And what I like about Malkin's work is he always took it back to first principles. He didn't say, hey, we did a bunch of tests and here are the results. He said, here's a bunch of tests, here are the results. Now let's look at that based on what we know fundamentally is happening at the grit workpiece interface. What is the grit? Is it rubbing, cutting, or plowing against the workpiece? And then basic heat transfer, basic forces, F equals ma, all that stuff. And he always took it back to first principles. So I would say if you're working in grinding, especially in academia, you need to have a good handle on the Malkin stuff. If you're working in CBN and diamond, you might say, oh, he did most of his work in aluminum oxide. Don't be a grinding snob. This guy did work mostly in aluminum oxide. He did very good work in CBN and some work in diamond. But grinding is grinding. The fundamentals are the fundamentals. The contact mechanisms are pretty much the same. The only difference is some materials are harder than others. So I would say, even if you're working with diamond and CBN, learn the grinding, learn the Malkin papers. This is Malkin's first ever paper, well, at least the one I'm aware of. Maybe he did some before this, I don't know. But this was based off his PhD work at MIT. Now, he had moved to University of Texas at Austin, my alma mater, Texas Longhorns, and he wasn't there for that long. But when he wrote these papers, he was a professor at University of Texas at Austin. And this paper is actually a two-parter, so we're going to do it, both of them. We have it in one file here. So it's a two-part paper, part one, part two, and I'm just going to call I'm going to consider it one paper. This will be series one. Wear of grinding wheels, part one, Attritious wear, and then he got into part two, which was fracture wear. So how are the grits wearing away? And Attritious wear is the tip of the grit just wearing away slowly, either through abrasion or chemical processes. And then part two is fracture wear, where the grit itself fractures or the bond fractures. And I'm not going to spend a lot of time going into details. A lot of the stuff in my book of grinding if you take my course, my 6,000 page book of grinding, a lot of it is stuff pulled from here. So I say, okay, Malkin did fabulous work. Let's change it around, make it a little less academic, make it more accessible, add in some pretty pictures, add in some color. And I use a lot of the Malkin stuff in my educational work. And of course, I credit him. And so he did a bunch of stuff with different grades of wheels, talks about the bond percentage here. Let's see, talks about the bond percentage of the different grades. And doesn't mean your wheel, your H or IG or JG wheel is going to have the HIJ wheel is going to have the same percentage, but he's given his numbers, and Malkin is just concise in his writing. He tells you everything you need. If you needed to repeat his experiment, you could probably pull it off just with what he tells you. And he's very concise about it. He goes, okay, here's exactly what we did. And I get frustrated with other papers because I say, oh, what wheel speed did they use? Or what kind of dressing diamond did they use? And they don't tell you. So here we have Malkin's forces. So he has the normal force and the tangential force. As he continues to grind, he did it for different wheel grades, GHI, JK. And then he saw, okay, what happens as the grits self-sharpen, as they bust out of the bond material in the G grades, where in the K grades they don't. He did the normal force and the tangential force, and then he did the ratio, which is very nice. I appreciate that, because what this paper taught us is that as the wheel dulls, the tangential force goes up, but the normal force goes up exponentially. And I show that in my book of grinding, where if we double the tangential force due to dull grits, we double the heat generation. According to the Jaeger equation, we also double the grinding temperature, more or less, but we don't double the normal force. And in Malkin's case, the normal force went up by a factor of 7. So double the tangential force means 7 times the normal force. And 7 times the normal force is a killer in terms of deflection, chatter, bad things happening. Okay, and then here we have a figure 3 where we see, okay, the wear flat area percentage, and this is why there's just so much you can suck out of the now Malkin paper, because the wear flat area percentage is different even for different grades, because the grits are surviving or dying based on getting pulled out based on how much bond material there is. And then we get more dulling, and then we can see how that dulling changes over time. And then we can see how the G wheel, it's going to dull also, but the grits are going to pop out. And I pose that in my grinding course as one of my trick questions. Are the grits in the K wheel dulling faster than the grits in the G wheel? And the answer is no, they're not dulling faster. They're just, the grits in the G wheel are popping out. And so we spend a bit of time of that in my course. And then we have the wear flat area. Malkin built this little wear flat gizmo to measure the area of the wear flats. And then you can see the wear flat area is getting bigger or not getting bigger because the grits are popping out because of the less bond material, but they even start at a higher level. That's significant right there. Okay, that tells us something. And then over here, he gets into I haven't looked at this in a while. Okay, he's got cutting point density, grains per square inch. And then Malkin was smart to divide it between cutting point density or grain density. Some researchers don't do that, but there is a difference because you can have multiple cutting points on a grain. And then he looked at the cutting point density for different wheel grades. And, you can dissect one of these Malkin papers and probably write 3 papers just from this data, because you say, okay, well, why is the wear flat area bigger, but the cutting point density isn't bigger? But then does that mean that we still have a sharp wheel for a short period until they dull, but they dull more quickly? There's a lot going on here. And here we have a picture that didn't come out very well. I think that's one of his wear flats. And then we have the normal force and the tangential force. And then he talks about something catastrophic happening when the wear flat area gets about 3.5%. And boom, the tangential force starts going up, but the normal force goes up in a huge amount. What's going on here? Now, there's a lot. I wrote a whole paper on wheel collapse, where your wheel goes chunky. based on this concept, similar concepts, interesting stuff. And then the ratio of the normal force to tangential force goes up. And then this is also about the time when you get burn, and he defined burn as rehardening, newly formed martensite. So then why is that? And then possibilities of material adhering to the tips of the grits, stuff like that. Okay. Then we have the, let's see, I think that's just a different material. We got the same thing going because that's 52-100 versus 1018. And same thing. Oh, now he's plotted it versus wear flat area. Yeah, that's what he did before too. And then he did more wear flat area force. Same thing, different materials, different dressing conditions. And he was thorough. He measured surface finish and how that was changing, not changing as much as you might think with the dulling of the grits. So there's a lot to take in there too. You say, well, the grits are becoming dull. The surface finish should be getting better. Well, maybe a little bit, but not as much as you might be inclined to think. Okay. And then he got into the mechanics of it, as you should. Just basic, some of the forces, chip formation. He broke it into cutting force, plowing force, and rubbing force. Then he gets a little bit into the tribology of what's going on here. The pressure's going on, and he got into, okay, is it that pressure a function of the wear flat area? And all legitimate hardcore tribology stuff here. And then he published the results. I mean, this is what I like, because you can, if you want to reproduce it, you can reproduce it. Puts his data in here. Then he got into the cutting energy. This gets a little complicated because Malkin claims there's a minimum cutting energy that's independent of your parameters. It's independent of your dressing. It's just you've got, and I think he had 13.8, I think was the value he came up with. But we had tests later that said, no, you can actually get lower overall grinding energies if you have a super sharp wheel aggressive. And so this might be one of the few cases where someone said, all right, Malkin, you're doing well, but we found some different results and we're not sure we agree with you. And then he also got into the melting point. There's another one. I was never a huge fan of this, which is rare for a Malkin paper because I usually just believe Malkin. Even if I don't understand him 100%, I go, all right, I believe you. Or even if I disagree, I go, yeah, I don't know, you still might be right, even though I disagree. Unless I have a really good handle on why I disagree. He gets into burner. He mentions Tarasov right here. He talks about temper colors. One of the few researchers that, especially back in these days, who had an understanding of the difference between what is discoloration of the workpiece versus over-tempering versus residual stresses versus rehardening burn. All good stuff, okay? And then he gets into the wear of grinding wheels. Now we're not talking Attritious wear or dulling. We're getting into grit fracture, bond fracture. It was all part of the same Ph.D. work, and Malkin ground, and then he collected the swarf after grinding the wheel wear. He collected the swarf, and then he took out the, I think he dissolved away the swarf and only got the little bits of aluminum oxide, and then sieved the pieces of aluminum oxide to see how big the grinding swarf was. This kind of blew my mind, but that's what he did. And then he did it for different grades, G, H, I, J, K, and you can say, okay, you know, we're going to get more wear with the G wheel, obviously, less wear with the K, but he didn't just leave it at that, as some researchers might do. He did what he should do. And he saw that, okay, it's not necessarily goes in order, G, H, I, J, K. You can actually get more wear with a K wheel. I don't know if that's the one. And then he sieved out the dressing particles, but that was a different paper. This is still the wear particles in grinding. Sieved them out, and what this showed, oh yes, okay, and he did a distribution. And so this is a distribution of, cumulative distribution of, okay, how big are the grains in the wheel, and then how big are the particles be collected, and is there a difference between the G, H, I, J, K wheels? And he found, all right, well, look at this. When we have a G wheel, the grits are all pretty big, which means the grits are busting out of the bond material. When we have a K wheel, the grits distribution, the size of the particles is smaller because the grits are busting out of the bond material, yes, but they're also fracturing in little bits and pieces. And you might think, well, no shit, Sherlock, of course that's the way it is. That's what's going to happen. But in 1969, we didn't have a handle on it. And we need to. We need to have a handle on these things. And then dressing, then he collected the dressing particles. I think he wrote a whole other paper on this and how big the dressing particles are, because is dressing a G wheel the same as dressing a K wheel? And the answer is no. The wear mechanisms of the wheel when the grits come out are different for the G and the K, because the G wheel, the bond is going to fracture and occasionally the grit's going to fracture. Where the K wheel, the bond is going to fracture occasionally, but the stronger, but the grit is going to fracture more often, and we're going to get a different distribution. Okay. And here he is. He breaks down what that is, the percent of bond fracture versus the percent of grit fracture during dressing. And then did it the way you should do it too. Said, hey, there wasn't much of a difference between the sharp dress and the dull dress. Is that right? Yes, I think so. And here we have the same. And then he starts getting into some stresses in the grits. And I've dabbled in this too. This gets messy. He has this bond stress fracture, but he's doing what he should do, and he's evaluating that. And then things get interesting because you have this minus sign here. So when you have a bigger normal force, you actually induce these kind of quasi-compressive stresses, which would lower wheel wear. But then normal forces go up exponentially when your grits become dull. And that's one of the reasons why when your wheel becomes dull, you don't necessarily get a lot more wheel wear, because you get these compressive stresses that are in there that actually don't help the bond fracture, except when they fracture catastrophically and very quickly. So that's interesting stuff. And here he has his bond stress factor. Malkin's data always lines up perfectly. Blows my mind. Anybody else, I might think, come on, buddy, you're massaging your data. But Malkin's so thorough that I doubt he was massaging his data. I think he just set up a very good experimental rig and got good data. So that's it. And then we got some conclusions. This video is probably longer than I planned it to be. But so this is the original granddaddy of Malkin's papers, maybe his best paper, or maybe one of his best papers. But he had several years of a Ph.D. involved in it. Got several papers out of that Ph.D. And we still use this today. I use it when I have my grinder's toolbox. I use a lot of these fundamental concepts, equations. When I teach my grinding course, I pull from here. If you take my grinding course and you look in the book of grinding, you will see a lot of similar graphs, maybe not exactly the same, because I change them around a little bit to make them a little less academic, a little more user-friendly. And then I put red and blue and make them look pretty, and add Joe the grinder and Bud the button pusher. But I use this to explain the fundamental concepts in grinding, which we got from Malkin back in the 1960s. So this is Jeff Badger, the Grinding Doc, talking about the great papers of Stephen Malkin, grinding guru.